Hi guys, this is the last section of our chapter in Unit 4, Section 4.3, Inverse Functions. The objectives in this lesson are we're going to look at functions and determine if they're inverses. We're going to see if a function is one-to-one or not. We're going to find the inverse of a function in its graph, and then we're going to talk about inverse functions on limited domains. Okay, so first we need to talk about the definition of a one-to-one function. So a one-to-one function is where each y value in the range corresponds to one x value in the domain. So actually, let's review a little bit first what the definition of a function was, which is what we talked about earlier in the semester. A function is where each x has exactly one y. And remember, we did like a vertical line test to check that something was a function if you're not sure. A one-to-one function is a special case of a function. If something's a function, if each x goes to one y, it's also a one-to-one function if each y goes to one x. So we can look at it in both directions. So we're going to look at these three little diagrams at the bottom here. These are called correspondence diagrams. And we want to determine, number one, just if each of them are a function. So again, just review from what we talked about earlier in their semester. So let's look at this first diagram here. We have our set of domain elements, which are our x's, and our set of range elements, which are our y's. If we're looking for something to be a function, we want each x to go exactly to one y only. And you'll notice that x2, that x value, goes to two different y values. So that makes it not a function. Okay, so that was the test we were looking at before. All right, let's look at the middle diagram. Here again, we're looking, is it even a function? Does each x go to exactly one y? And the answer is yes. Each x has one y value that it corresponds to. x2 and x3 go to the same y value, but that's okay. They each go to only one. So we would label this as a function. Each x has exactly one y. And then let's look at the third one. Again, I have my domain and range elements. Again, we're looking for, does each x go to exactly one y? And the answer is yes. There's nowhere here where we have one x that goes to two different y values, so it's a function. All right, so now we want to know, are these functions one-to-one functions? Well, the first diagram isn't even a function, so we're not even worried about if it's one-to-one or not. It has to be a function first. Let's look at the middle diagram. So the middle diagram, each x goes to exactly one y, and now we want to look at it the opposite way. Does each y match up with exactly one x? And you'll notice we have kind of the opposite problem from what we saw earlier here. If you look at y2, y2 is paired up with two different x's if we're looking in this direction. So we have one y with two different x's. So we say that this is not a one-to-one function. It's a function, but not a one-to-one function. And then let's look at the last one. We already said each x goes to one y, and now if we look the other direction, does each y go to one x? And the answer is yes here. There's no y values that go to two different x values. So this is an example of a one-to-one function. Now, why do we care if a function is a one-to-one function? Well, we care that it's a one-to-one function because it means it's invertible, meaning it has an inverse and we can calculate the inverse, which is kind of what we're building up to in this section. Okay, another way to tell if you have a one-to-one function or not is with the horizontal line test. So remember, the vertical line test is what we use to determine if something was a function. A horizontal line test can then be used to determine if we have a one-to-one function. So let me make a line here for us to kind of move around a little bit. Let's just make a vertical line here to start, okay? So first I want to see if any of these are, I want to check that they're functions first, because remember, it has to be a function to be a one-to-one function. So I'm going to do the vertical line test. Vertical line test is I drag this vertical line across my graph and it only touches one point at a time. It looks like graph number 1 passes our test, so it is a function. If I look at graph number 2, again, if I drag it across the graph, this line is only touching one part of my graph at a time. So yes, it's a function. And then graph number 3, the green line is what we're looking at here. We are only touching one part of the graph at a time. So yes, it is a function. So you want to check that first before you do the horizontal line test. Okay, so let me see if I can make this a horizontal line. There we go. All right, and we're going to do the same thing now. Only difference is instead of dragging it left and right, I'm going to drag it up and down. So I'm going to drag this up and down, and I only want to touch one part of my graph at a time. And you can see somewhere like here we have an issue. Right now my blue line is touching 3 different parts on the graph. So this is not a one-to-one function, and we'll label that in a minute. Okay, same thing with the middle one. If I drag it down somewhere like here on my parabola, it's going to touch 2 parts of the graph at the same time. So not a one-to-one function. Let's look at the third graph. If I drag my line down, you can see I'm only touching one part of the graph at a time. So let's label them. It's a function, but not one-to-one. This guy's a function, but not one-to-one. And the final one is a one-to-one function. It passed both my vertical and my horizontal line tests. Now, sometimes when we're talking about inverses, we want to be able to calculate the inverse of something that might not pass the horizontal line test. So what we do is we restrict the domain. For example, let's say I look at this middle graph, and let's say I took away this whole side of my parabola. Okay, so I'm only looking at the parabola for x values greater than or equal to 0, meaning from the origin and everything to the right of it. Now, if I do my horizontal line test, it passes my horizontal line test if I'm not looking at that left side. So you're going to see some things like that pop up in some of our problems where next to an equation you might have something like this, and that's just restricting the domain so it makes sure that our function is invertible. It has an inverse. Okay, so let's look at the actual definition of an inverse now. The definition of an inverse f is called the inverse function of f, where f is our function. Again, it has to be a function, it has to be invertible. The notation that we're going to use looks like this. There's going to be a little -1. It almost looks like a power, but it is not an exponent that we're calculating. It's just notation. And when you see it, it's usually going to be between the name of the function and your parentheses, where your variable, your independent variable is located at. The definition of an inverse says that if I have f of x equal to y, which is our regular old function notation, the inverse says that f inverse of y equals x. Now notice the difference here. In this notation, my x and my y have changed from what they started with, and that's really the definition of an inverse. All your x's and y's switch. All your domain elements and all your range elements switch. So if you want to calculate the inverse, and let's say we just start out with an easy one here, f of -3 equals 12. So it's a regular function. What's inside my function is an x. What's outside my function is a y. Okay, so really what I'm given here is some point, -3, 12. If I want to calculate f inverse of 12, when we're talking about the inverse now, what we see inside the parentheses is the y. And what we're calculating is the x. Well, I already knew the x. The x was -3. So that's the answer to this problem. F inverse of 12 equals -3. It tells me in the regular function, if 3 is the input, 12 is the output. And so the inverse is the opposite of that. If 12 is the input, -3 is the output. Okay. And then again, there's a little note to the side here just telling you that -1 needs to look like this in your notation. We're not going to put it outside of the parentheses there because that instead would mean a negative exponent and a reciprocal. You'd have to put it in the denominator to make it positive and other things like that that we've talked about. Okay. All right, so let's look at some correspondence diagrams here. We want to know, number one, do they have an inverse? And to figure out if they have an inverse, that's just that one-to-one question we were talking about a minute ago. And then if they do have an inverse, we want to be able to calculate it. Okay, so first let's look at these values. My domain elements are 2, 5, 3, and 7. They're all different, and they each go to 1y. 3, 4, 1, and 8. Let's look the other direction. So that tells me so far it's a function. So far so good. Each x has one y. Let me label that x and y. Let's look the other way now. Does each y have one x? 3 only goes to 2, 4 only goes to 5, 1 only goes to 3, and 8 only goes to 7. So yes, we have something that's invertible, a one-to-one function. Now, if I want to say if it has an inverse or not, my answer is yes, because it's one-to-one and has an inverse. If I want to calculate the inverse, all I have to do are flip these values. So I'm going to do it in a table. Okay, again, this was an x and a y, so if I want to find f inverse, I'm flipping it. It's a y and an x. Y's are my input now, 3, 4, 1, 8, and x's are my output, 2, 5, 3, 7. And when you graph these, they won't be y and x anymore. There'll be an x and a y, but for the inverse function. Okay, but notice all we did there was just flip all the domain and range elements. So now let's look at number 2. Again, domain is my x's, range is my y's. Let's see if there's an inverse. Each x, 4, 8, 13, and 18, goes to one different value of the range. So it's a function, yes. Let's look the other way now. Does each range element go to exactly one domain element? And you might notice that we have a repeating range value here, 7. 7 goes to 4, and 7 also goes to 18. So my answer is no. It's not an inverse, and you could say it's not an inverse because of those 2 points. It's a counterexample. Those 2 points have the same y value but 2 different x values. So that makes it not one-to-one, and there is no inverse. Okay, so just a little more practice with our tables here. Here we have function g of x, and it's a cubic function, 2x to the third minus 1. We want to complete the tables below for g and g inverse. So let's just start with g. So g of x, just a fancy way of saying y. We have all of our x values, so we're just filling values into our equation. And you can see the first one is done for us. Negative 2 gets plugged into our equation. Negative 2 to the third times 2 minus 1 gives me negative 17. So now we can do the same thing with the other values. So if I wanted to find g of negative 1, I would plug negative 1 into this function. 2 times negative 1 to the third minus 1. And that's going to simplify to a negative 1 times 2. Negative 2 minus 1 is negative 3. Okay, if I plug in 0, 2 times 0 to the third minus 1 would just give me negative 1. If I plug in 1, 2 times 1 to the third minus 1, well, that's just going to give me 2 minus 1, or 1. And then if I plug in 2, then I have 2 times 2 to the third minus 1. Well, 2 to the third is 8, times 2 is 16, minus 1 is 15. And you might be noticing that these values look a whole lot similar to these values. And that's because the second table is representing our inverse. And remember, an inverse, all we're doing is flipping our values, flipping our x's and our y's. So in our regular function, g of x, the x's are negative 2 to 2, and the y's are negative 17 approximately to 15. In the inverse function, our x's and y's are switched. Our x's, our domain elements, are those negative 17 through 15 values, and our y's, or our range, are just the original x values that went with them. So pretty straightforward to calculate an inverse if you have a set of points. We're just, remember, flipping our coordinates, flipping our domain and range elements. Okay, so let's talk about the graph of an inverse now. Same definition applies here. If we have a graph and we want to find the inverse, all we're doing is flipping our x, y coordinates. Now, what that looks like if we flip x, y coordinates, this is review from maybe like a geometry class if you've done that before, is when we take a point x, y and make it the point yx, if we flip those coordinates, that is the same as reflecting over the line y equals x. It performs a reflection. And the line y equals x, and it's written up here, is the same as y equals 1x plus 0. It's a linear equation with a slope of 1 and a y-intercept of 0. So you could sketch that here. Y-intercept of 0, rise 1, run 1, slope of 1. Okay, so that, just kind of do it this way here, is the line that all these points are going to reflect over. Okay, so here I've got some points labeled for you already. All we're going to do is switch our coordinates. So we'll start with negative 5, negative 2. If I want to find the inverse of that point, I switch the coordinates. So it becomes negative 2, negative 5, and I'll label it. Okay, and you can see that reflection that's happened here. Okay, actually I might have labeled mine 1, 2, 3, 4, 5, 6. Mine might be a little bit low. I think I went one too low there. Let's see if I can, oops, no, don't do that. There we go. Just move it up a little bit. There we go. Perfect. Okay, so let's try the next point. The next point is -1, -1. Well, if I flip the coordinates, -1, -1, it actually stays -1, -1. And you can see why it would remain the same. If I reflect over this line y equals x, and I'm on that line, so it's not moving at all. The same thing's going to happen with 8, 8. We're on that line y equals x, so that point will remain the same. Finally, 3, 6 will become the point 6, 3. 6, 1, 2, 3. There we go. Now if I connect my points in the same order they're graphed in the original function, what you see in blue here is the graph of the inverse. So you might see some problems in MyMathLab where all these graphs are done for you and you're looking for that reflection over the line y equals x. Okay, so kind of be thinking about that when you're doing these problems. Think about that reflection as a mirror image. If you can draw that diagonal line from corner to corner in your plane, and you can see a mirror image of the graph over itself along that line, then you know you have the inverse. Okay, so here's a couple practice problems for you. We want to determine if the following functions are one-to-one. So think about that definition. Each x should have one y, and each y should have one x. So you're going to use that for A. For part B, my hint there is to graph it. Use your calculator to help you if you're not sure. And then part C, you have the graph. You want to determine if it's one-to-one. Finally, at the bottom, you're going to sketch the graph of the inverse, and I'll label these points here. I know it's a little bit tiny for you. So the first point is -6, 0. The second point is -1, 2. And the third point is the point 1, 7. I want you to find the graph of the inverse. Go ahead and take a second and do that. Okay, so in number 1, we're trying to figure out, or A, I guess here, if this is a one-to-one function. So we're going to look at our x's. 1, 2, 3, 4. Each x has one y, so yes, it's a function. Then we want to look at our y's. 5, 6, 7, 5, and it looks like we're going to have an issue with 5. 5 goes with 4, and 5 also goes with 1. So the answer is no. This is not a one-to-one function because you have one y value that goes with 2 different x values. The next problem, you can just get a quick sketch of it in your calculator, and I'll just put one on here for you instead of bringing up my calculator. X minus 3 to the third. This graph, here's my axes, is going to look something like this in your calculator. Okay, so we want to determine, is that a one-to-one function? So we're using the horizontal line test, and let me pull up a line that we can use. We're going to use it for a couple problems here. So if I do the horizontal line test with this problem, and if you guys have this graphed in your calculator, maybe you just like took your pencil or something like that and dragged it up and down, but you can see we only touch one part of the graph at a time. So yes, this is one-to-one. Same thing with C. If I do my horizontal line test, the answer is yes, that is one-to-one. So let's go ahead and label those. Yes and yes. Finally, sketching the graph of the inverse, -6, 0 becomes 0, -6. -1, 2 becomes 2, -1. And finally, 1, 7 becomes 7, 1. And there is the graph of your inverse. And again, they've got it sketched here for you, that line y equals x. You can see that mirror image of the graph over that line if we cross over that line or flip it over that line. So that's a great way to check that you have the graph of an inverse when you're working on your homework problems. Okay, so let's talk about verifying if two functions are inverses of one another or not. The reason that we did composition in the last section was because we use composition to determine if we have inverses. Two functions are inverses if, when you plug them into each other, so plug G into F and plug F into G, both times you get out x, just the variable. That's your proof that you have inverses. If you get anything other than x out, 2x, x to the third, x plus 5, they are not inverses of one another. So let me show you what this looks like. We've got two functions here down at the bottom, and we want to determine if they're inverses. So we're going to do composition both ways. And it doesn't matter which one you start with. Okay. So f of g of x means plug g into f. So function g is getting plugged into function f. So that means we're taking the x out and we're putting cube root of x in its place. Now we know a cube root and a cubed cancel each other out. So we are just left with x. So far so good. Now let's try it the other direction. You have to do it both ways. Sometimes it'll work with one and not the other. So here, if I see g of f of x, that means plug f into g. So we're going to take x to the third and plug it into where we see x in function g. So that would look like cube root of x to the third. And again, we know that those cancel each other out, or you can write it like we practiced, remember, with rational exponents. It would be a 3 over 3, which simplifies to a 1. So either way, it's just going to simplify to x. So this is what we're looking for to have inverses. If it simplifies to x both times, they are inverses of each other. If you get anything else, they are not inverses of each other. Okay, so let's try the next one. I might need a little more space. Move that down a little bit. Oh, no. That's not what I want to do. There we go. Let's get a good color here. Let's try purple. All right, so here we're going to do, again, f of g and g of f. So I'm going to start with f of g of x, which means plug function g into function f. Okay, so this is going to get a little kind of strange looking with our variables and our denominators. So I'm going to start with 1 over. I'm going to take that x out, put 1 over x plus 5 in its place. And then don't forget the minus 5 that's up there. Okay, now we're just going to start simplifying. Minus 5 and plus 5 can just cancel. So I have 1 over x. Then I'm going to think of this, instead of dividing by a fraction, I'm going to multiply by the reciprocal. Those are equivalent operations. So instead of 1 divided by 1 over x, I can do 1 times its reciprocal, which means just flip it, x over 1. And 1 times x over 1 is just x. So that's what we're looking for there. Now if we do it the other way, g of f of x, and I'll do this one in a different color, do this one in black. Here we're plugging all of function f into function g. So that's going to look like 1 over, and then in that denominator I'm going to have 1 over x minus 5 plus 5. Okay, and now again, I have a fraction divided by a fraction, which I don't love, so I'm going to rewrite that. Right, as 1 times, instead of dividing by that fraction, I'm multiplying by its reciprocal. The 1s are just going to go away here, so I'll have x minus 5 plus 5, which leaves me again with x. So x both times, yes, they are inverses of each other. Okay, so here are a couple for you to practice. In both problems, you're going to do f of g of x and g of f of x. And if you get out x both times, they are inverses of each other. If not, they're not. So these are just going to be yes or no questions in your Edpuzzle. If you're not sure and you want to check it, because pretty much the y's are alone in all of these equations, you can graph them in your calculator. If you graph them in your calculator, you should see that reflection over that line y equals x if they're inverses. So that's a good way to check. All right, so go ahead and try those. Okay, let's see how you did on these ones. So in the first one, if I plug g into f, that looks like 3 times x minus 1 over 3 plus 1. In your first step, imagine you have a 3 over 1 out front there. You have a 3 on the top and a 3 on the bottom. Those are actually just going to cancel. You have x minus 1 plus 1, which simplifies to x. In the second one, where we're plugging f into g, that looks like 3x plus 1 minus 1 all over 3. The first thing that cancels here are your 1s. When I simplify that numerator, I have a 3x over 3. And then again, the 3's cancel and it simplifies to x. So your answer should have been a yes for that one. They are inverses of each other. Okay, so let's look at the next one. If I want to find, we'll start with f of g of x. So that's plugging G into F. And hopefully you guys notice there's just these kind of restrictions off to the side. That's not really affecting our work here. It's just, you know, something that allows us to be able to find inverses. So we're going to plug function G into function F. So that looks like the square root of x minus 10, and that whole thing is squared, plus 10. The squared and the square root will cancel, leaving me with x minus 10 plus 10, and then my 10's cancel and I get an x. So far so good. Let's look the other direction. If I take x squared plus 10 and plug it into function G. So this is G of f of x. That looks like, in a big square root, x squared plus 10 replaces the x, minus 10. The first thing that's going to cancel are the plus 10 and the minus 10, which give you the square root of x squared, which just simplifies to x. So again, we get a yes. Both yeses, these are inverses of each other. Okay, the next thing that we're going to talk about is how to actually find an inverse. So we know how to determine if something could have an inverse. We know how to determine if two functions are inverses of each other. So now the last little piece of the puzzle is actually calculating an inverse. And we're going to use a 4-step process. The first step is, instead of an f of x, we're just going to put a y in our equation because we know those are equivalent. In step 2, we're actually going to get that inverse by interchanging the x and the y. So we know that's the definition of an inverse, is x's become y's and y's become x's. So we're going to make that actually happen in our equation. The x's are going to become y's and the y's are going to become x's. After that, you actually have the inverse. In step 3, you're just simplifying. You're going to get y alone in the equation. And then at the very end, instead of y, we're going to replace y with our function notation. So if it starts as a function f of x, we're going to replace it with f of x with that little minus 1 as an exponent between the f and the parentheses to show our inverse notation. So let's try the first one. All right, so let's try this first problem. We want to find the inverse of the equation. So let's walk through the 4 steps. Step number 1, we're going to replace the f of x, or whatever function notation we have in the equation, with a y. So y equals negative 2x plus 3. Step 2, we're going to switch the x and the y. So the y becomes an x, and the x becomes a y. And then from there, we want to solve for y, which just means get y alone. So we're going to move everything away from it. We did this earlier in the semester. So we're going to take this 3 and move it to the other side by subtracting 3 on each side. And then we're going to divide both sides by negative 2. And you can just leave it like this, x minus 3 over negative 2. And that leaves me with a y. At the very end, once your y is isolated, we're going to put back in the function notation we started with. So here that was f of x. And then between the name of the function and the parentheses, you're going to put a little negative 1 to show that is the inverse of the original function. If you wanted to check it, there are 2 different ways to check it. The first way is you can graph the original problem in your answer and look for that reflection that we talked about, or you can plug one of the functions into the other one to see if you just get x, that composition test. All right, let's try another one. Here we have function g. So the first thing I'm going to do is I'm just going to replace that with a y. I'm not going to rewrite the whole thing. We'll just say y equals x over x plus 3. And now I'm going to switch my x and y. So x equals y over y plus 3. Now in this problem we have a bit of a challenge getting y alone because there's 2 different y's. So the first thing we need to worry about is getting the y's together, and that makes it difficult when you have a denominator. So anytime you have a denominator in these problems, I would suggest first multiplying both sides by that denominator. Here the y plus 3's are just going to cancel, and I'm left with a y. And then over here I'm going to distribute my x in. So that would give me xy plus 3x. Again, I'm trying to get the y's together, so I'm going to take this xy term and subtract it on each side. So that leaves me with 3x equals, y and xy are not like terms, they have different variables in them, so I'm just going to write y minus xy, that's all I can do. And now I'm better, okay? I don't have any denominator, my y's are on the same side, but again I have 2 y's and I need a single y to get it alone. So we have a little trick. If you have them on the same side, you can factor out a y, undistribute a y, that common monomial factoring we've practiced. That would leave me with a 1 in the first term and a minus x in the second term. Finally, if I divide by 1 minus x on each side now, I have my inverse. So my answer is going to be 3x over 1 minus x. On this right side here, the 1 over x's cancel. And instead of a y, remember we're going to put back in our inverse notation. So this was g of x. And again, I'm going to put that little negative 1 there to show that it is the inverse of my original function. Okay. Let's try another one. Here I have h of x equals x squared minus 1. I'm going to start by replacing h of x with y, and now I'm going to switch my x and y. X equals y squared minus 1. Now this problem also has a restriction on x at the beginning, and we talked about that. This is a parabola, and that's restricting it to only half of the parabola. So we're also going to change that restriction. Instead of x less than or equal to 0, because we're flipping all of our variables, we're going to make it y less than or equal to 0. And why we're doing that is going to become clear in a moment. Okay, so now let's get that y alone. The first thing I have to do is add 1 to both sides. So then I have x plus 1 equals y squared. And then the next thing I have to do to get my y alone is take the square root of both sides. So on the right, I'm just going to have a y. On the left, there's nothing I can simplify there, but I do need a plus or minus. Square root of x plus 1. Now at the very end, we're going to put back in our function notation. Not an f this time. It was a h of x. Okay, so h inverse of x is what we've calculated. That distinguishes what we have from the original equation. And then let's talk about this y less than or equal to 0. Okay, that actually helps us with this plus or minus here. We only want what comes out of this equation to be less than or equal to 0, meaning 0 or negative. And that tells us instead of a plus or a minus, we only use the minus here, because we only want negative values to come out. If I only wanted positive values, you would see something like y greater than or equal to 0, and you could either put a plus out front or just nothing. But if we included both the plus and the minus, this would not pass the horizontal line test, and that would be an issue. Okay, so make sure you kind of look for those restrictions that might help if you have two things to decide between, like a plus or minus as you're solving. Okay, let's try the last one of these together. So again, I'm going to replace my function f of x with a y. And this is going to be very similar to the last one we did on the other page. So the first thing I'm going to do, actually, before that, let's switch our x and y's. That's going to be the first thing I do, is multiply by that denominator, because that's what makes this messy. Okay, so my y minus 2's are going to cancel. That leaves me with y plus 1 on this side. And on the other side, I'm distributing my x in. So that'll give me xy minus 2x. Now let's try to get our y terms on the same side. So I'm going to subtract y on each side. So that'll give me xy minus y minus 2x. None of those are like terms, so I'm just putting them next to each other. On the other side, I just have 1. And I only want y terms on this side, so I'm going to move the 2x over, get that away from my y's. So xy minus y equals 1 plus 2x. And now we can do our wonderful little factor step. I've got only y terms on this side, so if I factor out a y, I'll be left with x minus 1. And now I can get that y alone by dividing by x minus 1 on each side. So my answer will be 1 plus 2x over x minus 1, and instead of y, let's go back to that function notation. This was function f of x with a little negative 1 to show that we have an inverse. Okay. Again, if you want to check it, you could plug one function into the other, which might be a little messy for this one, or you can just graph the original equation and your answer at the same time and look for that reflection over the line y equals x. Okay, I want you to try these two on your own. Find the inverse. Okay, so I'm going to replace this with a y, and I'm going to flip my x and y. Let's solve for y. The first thing I would need to do is subtract 7 on each side. X minus 7 equals negative 5y. And then divide both sides by negative 5. So our final answer would be x minus 7 over -5. On the right, my -5s are going to cancel, and instead of y, let's go back to that function notation, f inverse. For number 2, again, replace it with a y, and let's switch our x's and y's. X equals 5 over y plus 1. Okay, as I said before, if you've got that denominator, a good first step is to multiply by that denominator on both sides. So that'll leave me with 5 equals, and if I distribute my x in, xy plus x. Okay, we only have one y here. Let's just get it alone. I'm going to subtract x on each side. So xy equals 5 minus x. And then I'm going to divide by x on each side. Again, trying to get that y alone. So y equals 5 minus x over x. And again, I can go back to my function notation, f inverse. And that's our final answer there. All right, let's try an application problem. I thought this problem was pretty interesting. It's about decoding messages using inverses. So let's say we assign numbers to letters of the alphabet as follows. And then 27 is going to be our blank space if we need it. Sorry, ignore the dog. We can convert a message to a numerical sequence. We can encode a message by plugging numbers into a function. So here's our actual example. Let's say we've got function c for coding, and my equation is 3x plus 2. So this equation has been used to encode a message. So they've taken the message, let's say the message was hi, so that would be h is 8 and I is 9. They plugged maybe those numbers 8 and 9 into the function, and this is what's coming out, all this list of numbers. So I'm going to write it out here. 41, 5, 35, 17, 83, 41, 77, 83 again, 14, 5, and 77. If we want to decode the message, we use the inverse. We want to figure out if values were plugged in and these were what came out, we want to be able to work backwards. We want to plug in the outputs and get the inputs, the original message. So we're going to find the inverse of function c. Again, I'm going to replace, write the function down here, c of x with a y to start. Okay, we're going to flip our x and y and then solve for y. So I'm going to subtract 2 and then divide both sides by 3. Okay, and that will leave me with the function x minus 2 over 3. If my 3's cancel, I'm left with y, and I'll just make it back to my original function notation, c inverse. So now to decode the message, we're going to plug each of these numbers, the coded numbers, into our inverse, and it should take us back to the original message. So let's start with 41, and we can just do mental math here, but you could always use your calculator if you needed to. If I do 41 minus 2, I get 39, divided by 3 gives me 13, and I'm going to do these in a different number, a different color, 13. Okay, if I plug in 5, 5 minus 2 is 3, divided by 3 is 1. If I plug in 35, 35 minus 2 is 33, divided by 3 is 11. Plug in 17, 17 minus 2 is 15, over 3 is 5. Plug in 83, 83 divided or minus 2 is 81, divided by 3 gives me 27. 41 we already had earlier, that was 13. 77 minus 2 is 75, divided by 3 is 25. 83, we already had that, that was 27. 14 minus 2 is 12, divided by 3 is 4. 5, we already had that one, it was 1. And 77, we already had that one, it was 25. So now if you look at the blue numbers, you should be able to use the code at the top to figure out what the message was. So 13 is an M, 5 is an A, or 1 is an A, 11 is a K, 5 is an E, and then remember 27 is a space. Okay, so I'll just put a little underscore there. 13 again is M, and then 25 is a Y, and then a space. and then 4 is a D, 1 is an A, and 25 is a Y. So the message that was encoded is make my day. Okay, here is a practice application problem for you. So X dollars are invested at 10% for 6 years, and here's how we calculate the value of that investment. The first thing you have to do is find the inverse. The second thing you have to do is figure out what the outputs represent, and my hint to that is look at the original equation and figure out what do the inputs and outputs represent in it, and then switch those to figure out what the inputs and outputs of the inverse function represent. And then finally, use your function that you find to do a calculation. Okay, take a few minutes and see what you can do on this one. Okay, so let's go ahead and find that inverse first. I'm going to replace s of x, my function notation, with a y. I'm going to switch my x's and y's. Okay, and now we are going to solve for y. In this problem, you can, you've got 2 different y values, so there's 2 things you could do. This is a 1y and a 0.6y. You could just add these together. Some of you may have factored the y out, and then you're left with 1 plus 0.6, but either way, you should get a 1.6 then y. And then to solve for y, you just divide by 1.6 on each side. So your inverse is x over 1.6 equals, and then instead of y, I'm going to go back to that function notation. Okay. All right, so that's part A. Part B says what do the outputs represent? So let's talk about the original function. In the original function, the inputs are X dollars that are invested, and the outputs are the future value of the investment, which is a fancy way of saying how much the money's worth after that 6-year time period. So if we want to talk about the inverse, we flip those. The outputs of the inverse are the same as the inputs of the original function, which are the dollars invested. Okay, and the inputs in the inverse then are the future value. So let's look at part C now. Use this function to find the amount of money that must be invested at 6 years for 10% to have a future value of $24,000. So remember, in our inverse, the future value is our input. So all we have to do is input 24,000 into this equation. And what we're going to get out is the amount of money that'll have to be invested. So you can just do that quick division in your calculator. 24,000 divided by 1.6, and I get 15,000. And then if you wanted to check that, you could plug 15,000 back into that original function s at the top and make sure it gives you 24,000 as a solution.